Gradients measure how quickly a graph is changing, its rate of change. So the gradient is the rate of change of a graph. For this graph here, how quickly the graph changes depends on where you are on the graph. Down here, where x is about -2, it's very steep. The graph is going up rapidly. The rate of change is large and positive. As I get closer to this small peak here, which is called a local maximum, the rate of change is decreasing. At this point here, it's 0. Then the rate of change is negative. We're losing value in y as x changes to a minimum value here. Then the y value starts increasing, slowly at first, and then much more quickly. The steeper the graph is, the bigger the rate of change. Positive means going up the hill from the left. Negative gradient is down the hill from the left. Positive again. So this graph has a positive gradient to here, a negative gradient between those 2 points, and a positive gradient up here. And then on forever. Here is another graph. This is a quartic graph, but it's got a bit of quadratic in it and a bit of linear in it. As I start from the left, if I'm coming down here, I'm rapidly coming down the hill, large negative gradient, till I get down to here, which is 0. So the gradient at this point is 0. Then the gradient is positive between this local minimum and this local maximum. Then again, it's gradient between this local maximum and this local minimum. And then it's positive again, and then on. So this graph has negative gradient from -infinity to this point, positive gradient between these 2 stationary points, negative between these 2 stationary points, and then positive again off to infinity. There are 2 main ways of getting a gradient. The first one is the average gradient. This is the rise over the run between 2 points. You need 2 points to get an average. If we have 2 points, x1 and y1, and x2 and y2, then the gradient between the 2 points is y2 minus y1 over x2 minus x1. So in this example here are 2 points. If I was finding the gradient between those 2 points, it would be an average, because I've got 2 points. And I would need to know the rise, in this case a negative, because it's fallen, and the run. And if I divide them, I'll find the gradient. The other sort of gradient is called instantaneous gradient, the rise over the run at a single point on the graph. It's the same as the gradient of a tangent to the graph. So at this point here, this straight line, which will have its own equation, y equals mx plus c, has a gradient of m. The gradient of this straight line is the same as the gradient of the curve at this point. But at another point like this one, the gradient of the curve is now different. In fact, at the top here, its gradient is 0. That's a local maximum. At another point over here, you can see the gradient of the curved graph is the same as the gradient of this straight line, which will have its own equation, y equals mx plus c, but m and c will be different than for this straight line. To get the gradient of these tangents, or the instantaneous gradient, we use calculus. So, gradient is the rate of change of a graph. It measures how quickly a graph increases or decreases. For a linear graph, the gradient is m in the equation y equals mx plus c. To get the gradient of any graph, we differentiate the equation that plots the graph. If I differentiate fx equals mx plus c, then the derivative is just equal to m. Well, that makes sense because we've already said that m is the gradient. If I've got this curve here where fx equals ax cubed plus bx squared plus cx plus d, then the derivative is this function here, 3ax squared plus 2bx plus c. This equation tells me how to plot the graph for any x value. It tells me the fx value or the y value for any x value, helps me plot the graph. This equation tells me the gradient for any x value. F dash x is the gradient, or how steep the graph is at that particular point. There are two equations, one to plot the y value for an x value and one to find the gradient for an x value. Now, for a graph, the gradient is so important because it's telling us how quickly the graph is changing that calculus is full of rules for differentiating equations. So here's some examples of some of the equations or some of the rules we use in calculus to find the derivative or the gradient, if you like, of an equation. Something to look forward to, hey?